Welcome. So we're going to kick off this week. We're going to continue talking about sets, and I want to talk about indexed sets. So we're going to take sets and we're going to take them to another level that we really haven't talked about in any of our previous situations, but they're going to make maybe a whole lot more sense now. So let's talk about index sets. So I'm going to have a collection of sets. So again, this is let's A, B sets, and I'm going to denote this alpha, where alpha is something in some other set delta. What do I mean by that? So I'm just simple. So this could be delta could be, you're used to things where delta is, let's say, integers. It could be odd integers, even integers. It could be just some list of things. So we're doing some kind of scripting to identify each and every one. If I want to do if so this is a collection where alpha is inside the delta. So this is a way of saying all this collection. If I use the a union, and I put the alpha is inside a delta, I'm saying for every pick any alpha in the delta and then union it with another alpha in the delta and another alpha. But we could also do an intersection. So these are the two key ways that we do unions and intersections of a massive collection here. And that's kind of critical. So let's do an example. I want to kind of illustrate this, and then I'm going to let you play with a couple examples to help you understand this. I'm going to do this where n is in the natural numbers. So we're starting at 0, and we could start at 0. I'm actually going to start at 1. Again, natural numbers, there's a huge argument. For this to work, and the reason I know that I have to start at 1 is this down here. If I plug in n equals 0, now this gets really weird because it's now 2. What I'm really trying to do here is create things that get funky. Oh, it went the wrong way. Um, it just can get really weird. So you have to think about the specific situation. This terminology in your textbook is going to actually be the natural numbers, not including 0, um, because that's how your book likes to do it, because it's more number theoretic. Again, any of you have taken number theory, in number theory, typically we drop the 0 because we're talking about modular arithmetic. It doesn't really work super well to have a 0 in terms of what are the possible. Just number theory doesn't like zeros, period, as a natural number. So, anyways, so this set, let's think about what this is. So let's just look at what this is so I can write this down. So this is going to be I1 union I2 union I3 union, and so forth. So in this case, I1 is going to be 0, comma 1 over 2 to the 0. Union 0, 1 over 2 to the first power. Union 0, 1 over 2 second power. Union, and so forth. Well, this is 0 to 1, union 0 to 1/2, union 0 to 1/4, union 0 to 1/8. Well, but notice, since these are all inside of this one, the truth is that union of n inside the natural numbers is equal to 0, 1. Now, if we allowed it to include 0, sorry, sorry about that. I had to pause to get a cough out. If I included 0, this actually, our first one would be 2. And that would still work. The idea still illustrates it. All right, so that's our first one. All right, so let's talk about what is the second one. Well, we just established what these are. So again, this essentially would be 0, 1 intersect 0, 1/2 intersect 0, 1/4, intersect 0, 1/8, intersect, etc. So let's just look at this pairwise. So these two, that intersection is, since this is inside of this one, it's actually going to be 0, 1/2. And now I would do, what's the intersection of these two? Well, it's going to be 0, 1/4, because 0 to 1/4 is inside of 0 to 1/2. Okay, what is that? Well, if we keep going on, that means all of these are actually going to be whatever is down this far end. But this keeps getting smaller. So this number is getting closer. So taking you back to your calculus days, the limit as n goes to infinity of 1 over 2 to the n minus 1 is equal to 0. But that's a limit. That's not what it actually is. So my upper bound and my lower bound are approaching each other and eventually going to be essentially the same. So what does that mean? Well, it actually means, if I get rid of all this, that this equals the empty set. Because eventually this would equal 0, 0 is what it's heading towards. But that means it has to be bigger than 0 and less than 0 at the same time, which is completely impossible. So it's going to be the empty set, because we're just getting rid of stuff every single time. It's not really equal to this, but this is the idea of where it's heading. It's kind of help you understand that logic. All right, so I want you to practice this and get kind of familiar with this. So I want you to try this one. Now notice, this is a little bit different. This is a sub n, where n goes, this notation here. Again, let's talk about what this means. This right here means n equals 1 to 26. So I'm going from 1 to 26, where A1 is the letter A, set with containing A. A2 is A, comma B, and so forth. With that in mind, what would be the union and the intercept? Oh, that's a type. This is a typo. This is a total typo. What that should be, it's not n with an n. That should be n between 1 and 26. That is actually what that should be right there. And same for below. But if I do the intersection and the union of all these sets, what does that look like? All right, so that's one problem. I want you to just practice that. Here's another one that's a little bit harder. So I just want you to get familiar with these ideas. So these are actually going to computation. We're going to move away from proofs for a little bit. But I need you to play with them to understand how we utilize these ideas. So let S sub n equal any real number x where x is contained in the set n minus 1 to n. Now, this is the notation here. Now, let's talk about what the heck does this notation mean? This. Well, again, what that literally means is this is going to be S1 union S2 union S infinity, except there's not really infinity. It's just that last part means it just keeps going on forever. So this is just like we do when we did summations. We've done summations in all your past classes, starting at the starting index and the upper index. All right, so I want you to do this one. What is that going to be for this situation? So S1, I'll give you a clue. S1 is equal to 0, 1. S2 is equal to 1, 2, because it's the number less than. And I did these brackets because these equalities do not have equality. All right, I want you to try this one. So you've had two so far. You need to do this alphabet one and this one. And let's go to 2.39. And I want you to do this one where R is any rational number. The NR be the set containing all real numbers except R. Whoa. So this one's actually really, really hard to do because there's a million rational numbers. Well, not million, there's infinite number of rational numbers. So what does that mean? Well, let's look at a couple things. Well, n1 is essentially going to be the set of all rational numbers. This is going to be set of all rational numbers except 1. That should be a squiggly bracket. n1/2 is going to be the set of all rational numbers except 1/2. And that's just positive. So again, I'm giving you these 3 problems to work on. I want you to get comfortable with how do you do this manipulation. And I want you to not just write down what it is. I want you to give a little bit of explanation. Put like a quick sentence or a pair or a couple sentences explaining why each of these, because this one especially, it's not easy to see. So that's your assignment, is to do these 3 problems and work through them and see what their infinite unions and intersections are.